let's dive in because welcome to Planet Geo, Professor Josh Davies. You are one of you have an amazing publication record, and I've told you this before, but you have a very, very impressive publication record. And I think just reading through the list of papers that you've published or you've been a part of kind of showcases the value of this deep geochronological toolkit. Like you have a tool in the toolbox that you're really good at, and your publication record showcases how many different problems this can be applied to in geoscience. And I want to focus today, if we could keep our conversation focused, Josh,
My fault. Sorry.
to one of them. I want to focus on one of them, which is calibrating the Earth-Moon distance back in geologic time, which I know is probably too deep for a single podcast episode, a single sort of 45-minute to hour discussion, but I want to try it. So the storyline here is that there are things called Milankovitch cycles, which we can briefly summarize what those are, that are climate cycles on Earth, on the modern Earth, and in the ancient Earth, going back many hundreds of millions of years. I think people can trace these. You guys thought, oh, there might be Milankovitch cycles in banded iron formations, which are layered sediments going really far back in time, but we don't know if they're there, and we don't know what the cyclicity is, what the oscillation time frame is. Like, is it 100,000 years? Is it 200,000 years? Is it 500,000 years? And so you had to go back, look at the cycles in banded iron formations, and then date the individual banded iron formation layers, or date the depositional rate of the banded iron formation, which you're kind of tackling two big scientific problems. Banded iron formations are a rock that are spectacular. They're of geologic interest. They're I mean, people know about banded iron formations. General people who don't know anything about geology know what banded iron formation is because it's a beautiful rock. Is that the origin? Like, what was the origin of this project that led to a couple very fancy publications in fancy journals? What was the origin of this? And what was the
It's a
workflow?
good question, actually. So for me, so this project that I worked on was a kind of really fortuitous collaboration between myself and the group in Geneva when I was a postdoc. That's when it kind of started, and a group in Utrecht University, which is in the Netherlands. So me and Urs Schaltiger, who was my supervisor for my postdoc, we wrote a proposal in Geneva. Yeah, in Geneva. So we wrote a proposal together where we kind of, with the lab in Geneva, specialized. I was a postdoc there on this high precision geochronology, and I've always been interested in the Precambrian, kind of old rocks, essentially, like understanding the history of the Earth. And there was people in Geneva studying Milankovitch cycles and climate and stuff like that in relatively young rocks, and I was interested in old rocks, so I was kind of wondering whether we could search for Milankovitch cycles in old rocks, and what that could tell us, essentially, about the climate back in time. Also, I mean, I'd heard about the fact that you could potentially calculate things like Earth-Moon distance if you can quantify the different periodicities of Milankovitch cycles. So actually, Urs and I wrote a proposal where we proposed, I think, 4 different time periods in Earth's history, all in the Precambrian, where we thought that there were.
And let me just jump in there, Josh. The Precambrian is before like 560, 570 million years ago. So we're back before multicellular life. We have far less of a rock record, and the rock record in the Precambrian is there's less rocks preserved from the Precambrian, and they're usually more altered and more deformed. So you don't necessarily have huge, thick sequences of sediment that's been completely undisturbed for their entire history, like you do in the Phanerozoic. Now I can go to the Appalachian Basins, and we can look at kilometers of sediment that is relatively undisturbed. You can't really do that going back in the Precambrian. So this is a difficult task, right?
Super difficult. And also, I mean, as a geochronologist, I need to be precise here with what I say. And the Cambrian boundary, as you should know, Jesse, is 539 million years.
Excuse me. Okay, yeah, we must be precise. Okay, that's precision at the 0.05% level, not the 2% level.
Exactly.
I'm a 2% precision kind of person, so Josh. So.
Oh dear. Oh dear. Oh dear.
536. Is that what you said? Is
539.
five? Oh, excuse me, 539. Okay, yes, I stand corrected. Okay, okay. So you,
Anyway, yeah. So exactly, but I mean, basically, what you're saying is right. I mean, the Precambrian rocks are often really they're really altered. They've been through different tectonic cycles. They're deformed, often metamorphosed, often, and so it's quite difficult to find nicely preserved examples. But I mean, as you know, and I know if you look around the place, there are certain kind of windows, well preserved windows of rocks in different places, and so we wrote a proposal about four of them, which are kind of well preserved. Actually, if I was to remember where they all were, I wouldn't be able to remember.
yeah,
One,
fair enough.
one was in Canada, one was in Brazil, definitely South Africa,
Which
and I
is one
think
of them you
Australia.
eventually ended up
Yeah, yeah.
going to,
So
right?
in the end, in the end, yeah. Actually, we were. What were the fortuitous thing was the Dutch collaborators. They were like actually written as collaborators into this proposal, but it turned out that they actually wrote a proposal at exactly the same time,
Oh, right.
and they
Okay.
focused on only South Africa and only Australia, and they focus on banded iron formations. And so banded iron formations was just one of the four options in our proposal. And so then, actually, once both of us got funded, we decided we were in contact after that, and we said, "Oh, why don't we go to the field together?" And so we went to South Africa. We went to a place called. I mean, it's kind of in the where is it? In the Central Cape, which is in northern South Africa, essentially northern central South Africa.
And this is a sequence of banded iron formations, I'm guessing, right? That you went to, and the goals were to look. Well, first of all, let's talk about Milankovitch cycles really quickly, because I think any intro geoscience student will have at least one lecture on Milankovitch cycles, and there are a couple different versions of Milankovitch cycles, but they all relate to Earth's orbit or Earth's kind of wobble and axis and tilt and things like that. So there's eccentricity, which is basically is the Earth's orbit a circle or an oval, and if it's an oval, how offset is it from the sun? It kind of wobbles a little bit, and that has about 100,000 year cycle today. Obliquity has about a 41,000 year cycle, and then axial precession, which is kind of the wobbling of the top, is about a 26,000 year cycle. And so those cycles are current. Well, that's what it's on Earth today, and in the recent past, I mean, I think people pretty convincingly. I'd be curious how far back we think those cycles exist in the rock record at those levels, but is it safe to say tens to maybe hundreds of millions of years those kind of cycles map into the rock record? I mean, people use this for geochronology to go back and they actually count the 100,000 year cycles to get back, many millions of years ago in the rock record. I mean, that's an accurate statement?
Yeah, I think so. I mean, actually, we need to again be precise here. These cycles, so like eccentricity or precession, obliquity, these are the names of them. As you're saying, I mean, we have to think about these periodicity as like changes in amount of solar radiation that the Earth is having, essentially. So eccentricity, like you said, is kind of how circular or oval the orbit of the Earth is around the Sun. And so if it's oval, it means that at certain periods as the Earth goes around the Sun, it's further away. And that means that at that time when the Earth is further away from the Sun, because the orbit is more oval, it's actually receiving less solar
That's
radiation.
right. So
Therefore, it's a little colder. And so
So
that's
is
kind of,
it?
yeah, yeah.
I forget which orientation it works, but is it the southern hemisphere summer is cooler when it's more eccentric orbit or something like that, or the northern hemisphere summer is cooler because it's further away in that part of the orbit around the sun, or something along those lines, right? Yeah. So and that'll oscillate, but these 100,000 year cycle, 41,000 year cycle, 26,000 year cycle, they work together, right? So sometimes they fight against each other with the amount of radiation that's hitting any point in Earth. And sometimes they feed back positively with each other. So we end
Well,
up
that's
with,
actually
yeah,
well,
go ahead.
yeah. I don't want to cut you there, but
No,
I mean
please
that's
do.
actually an extremely important point. There is basically actually, so there's the three cycles: eccentricity, obliquity, and precession. And eccentricity and precession, those are the two that interfere with each other, essentially. So they've got different periodicities, but when you see a big signature of eccentricity, you also see a big signature of precession. And so when you see eccentricity is small, precession is small.
Okay.
So
Gotcha.
those two cycles interact with each other, whereas the obliquity cycle is more consistent and kind of on its own.
Okay. It's kind
So
of separate.
obliquity
Okay. All right.
is the
Good.
tilt.
Okay.
Precession is the spin of the axis, the kind of wobble of the axis, and then eccentricity is the whether it's circular or oval.
Okay.
There's other ones
Interesting.
as well, but
Yeah.
what's kind of cool is that there's these kind of models for how all of these cycles interact and how they have changed back in time. So this is kind of the start of the story, I guess, a little bit, is that these models, there's these very clever astrophysics people. I mean, I've seen them, but I mean, they're too clever for me to speak to.
They're physicists ultimately.
They're very
Yeah,
physicists. I
they're
mean,
too
so
clever for anybody to speak
they're
to.
made too
Yeah.
clever for me.
They're
So
too
they've
clever
made
for me
these
to speak.
models. They and they've made a model of kind of how these things change over time. And so we're speaking about like astrophysics stuff. It's about gravity, and so all of the other planets are involved in these Milankovitch cycles. They
Yeah,
actually
like you Jupiter,
really
Neptune matter, right? These
yeah,
huge
yeah, yeah.
gravitational wells way out in space. So one more data point about the modern Earth, then we can get into the story, is that we know pretty well, we can watch it happen basically, is that the moon is moving away from the Earth by what? It's like 3 centimeters a year, 4
About
centimeters a
three
year, or something.
centimeters a year.
3 centimeters a year. Okay. It's moving away from Earth. And we know that that can't have been happening for all of geologic time. That's not a constant rate, because if we just calculate that backwards and say, oh, the moon has, let's say it's been moving towards Earth 3 centimeters a year back in time, it would have been at the Earth like 1.5 billion years ago. Is that right? Or something in that order?
Yeah, exactly. I mean,
Which,
because
which we
actually,
know is
yeah,
not true. We know the moon is at least 4.3 billion years old. And so clearly the rate that it's moving away from Earth right now has not been constant throughout all of geological time. And so the question begs itself: what's going on with the moon? How's it been working in working with Earth's orbit here? So sorry to interrupt you there, Josh, but
no. So I mean, all I was going to say is that there's this really nice model that includes the recession of the moon, actually, and it includes changes in all of the other orbits of the different planets, and even comets and stuff coming through our solar system. There's a astrophysics model for how that all of that stuff relates to the incoming solar radiation on our planet.
in
That's
the
kind of if you
incoming solar radiation is climate ultimately, which
yeah,
climate equals
essentially climate.
sediments.
Yeah.
Inside climate equals weathering, climate equals rain, climate equals sediments. So we can
Equals
look at
glaciation and no glaciation.
right? So we can look at these a whole bunch of cycles in the Earth's system. We can look at rocks preserved back in time. We can look at mud logging from interglacial lakes and this kind of stuff, and see some of these records, right? So we could see this periodicity in these records because it's ultimately related to climate, independent of tectonics. Or climate on top of tectonics, like an additional forcing on top of the sort of climate cycle on Earth. So, all right, sorry, your model, this astrophysical
The
model.
cool thing is this model, we've got this really nice model, and it goes back from today, essentially, back 60 million years, maybe 55 million years. And so actually, if you look at the model, there's basically the model is a kind of curve. It's like a wiggly curve with all of these different cycles all included in it. And you can compare that curve to the rock record. And the match is like, it's really astounding. I mean, it's amazing. The rock
Back
record...
50 million years, you said, or 60,
about
somewhere
50,
in there?
about
Okay.
50 to 60 million years.
Okay.
It matches really well. But after that, it doesn't match at all. Actually. It just...
Okay.
doesn't match.
Okay, goes
so
haywire.
I mean, if if you look at some of these papers, like I say, they're too complicated. It goes crazy. It's not. There's this kind of chaos in the system. They don't really know why.
Okay. I mean, okay, we're being a bit facetious here about the physicists, but it's pretty impressive to get 50 million years on Earth really, really accurately right. But then if it goes haywire, obviously we have a problem, and we're not understanding something, right?
There's something in there that's not clear, but we can kind of assume that the Earth was still there before 50 million years ago. We can kind of assume that the sun was also there. I mean, these are general assumptions that, I mean, most people would be okay with, I would say.
Okay, good.
Maybe not everybody, but
I think I'm following. I'm tracking so far. Yeah. All right. I buy it.
So, I mean, we can blame the models. We can say that, okay, maybe there's a problem here with the models, but maybe we can actually look at the rock record to tell us something. Then you can kind of use the rock record to tell you something about like the physical state of the solar system. And there's a cool link, I mean, with precession, which is another thing it's that cycle, that's the wobble of the Earth's axis, that's kind of linked to the eccentricity, which is the orbit.
So this is the wobble, like Earth,
wobble.
the like
Earth
is a spinning
top one.
Spinning top, right?
Yeah.
And the precession is how much it's wobbling. Like it wobbles a little bit, then a lot, then a little bit, then a lot. Okay. Yeah. So the inception thing, where the top is wobbling, and it's kind of wobbling, and then it wobbles a little bit more, and then a little bit less, and they leave us hanging. Don't really know, whether the top fell or not, right? So it's that kind. That's the thing that we're talking about. That's precession here. Is that wobbles more or wobbles less? Okay. Sorry. So there's something interesting about precession. You were saying.
Well, there's actually a relatively simple calculation. If you can work out the periodicity of this change in precession, you can almost directly, with a simple calculation, determine the distance between the Earth and the Moon.
Oh, interesting.
Actually.
Okay.
So that's what we targeted, essentially, with our study, is that we wanted to see if in kind of relatively well-preserved sediments, in very, very old in Earth's history, we can find a signature of precession.
Okay. Interesting.
Because we knew that there's a relatively simple calculation you can do to just turn precession. And so the cool thing is also, if you get Earth-Moon distance, you also get another thing which is kind of cool, which is the length of the day.
Yes, and that's right. I remember reading this in your paper, and it's very cool. So let's leave that hanging for a minute, because I want to come back to that. Let's end with the length of the day. What did you measure? I mean, so you're going to these big banded iron formation patches, which are, as the name implies, banded iron silica interbeds is the typical one. You got an iron-rich layer, a silica-rich layer. And what are you mapping to capture the cyclicity? And then the second question is, how do you date that? And how do you tell what the length of the cycles are?
Yeah, I mean, it's a great question, actually. I mean, so we could speak for hours about banded iron formations.
Yes.
They're super. They're really fascinating. They're like super useful. They tell you so much about like the history of the Earth. I mean, really cool rocks.
And they're incredibly controversial too in the scientific literature.
Yeah. I mean, there's so many options for how they could be formed. Really crazy. But they're also very beautiful, as you say. What we did in our study was we kind of stepped back from a lot of the controversy. We didn't really go into detail about exactly how they were formed.
Okay.
We came with a hypothesis that there is cyclicity preserved in these rocks.
Okay.
That was our hypothesis.
That was it.
Okay, so we wanted to see if we could find it, if it's there or not.
Yeah.
And what we did was something really, really simple. I mean, much more simple than most people would imagine, based on the kind of fancy stories we managed to get out of this stuff. We did really simple stuff. So banded iron formations, like you say, they're kind of classically thought of as like layers, thin layers, kind of at the centimeter scale of iron oxide minerals like magnetite, hematite, which is just iron and oxygen, and then chert, which is silica and oxygen. So like iron-rich, silica-rich, iron-rich, silica-rich. But actually, if you step back from the rocks a little bit, I mean, when you're looking at banded iron formation in the field, if you step back, away from like really centimeter scale, there's also other stuff in there. There are kind of shaly units, which are like fine-grained siliciclastics. There's also kind of iron-rich carbonates. So it's not, when you speak about banded iron formation, everybody only looks, well, not everybody,
no,
but
but
people
most
really
people,
really concentrate on the iron and the silica
we
layers.
look at the
but actually there's
beautiful
other stuff there too.
silver and purple rock part, which is the
I mean, it's really pretty. It's rare. It's not rare, but it's really beautiful. Whereas actually above that and below that, there is kind of a more carbonate-rich area, or there's a more kind of siliciclastic area. I mean, all fine-grained rocks, but there's kind of less of the banded iron formation, classic iron silica, and a bit more carbonate. And then there's some areas with a bit more siliciclastics. And so actually, the banded iron formations, we went to go and see them in the field. The classic banded iron formations, they make up these kind of cliffs because the rock is really hard. And it's difficult. I mean, you can hit it with your hammer and it just bounces off. It's actually quite difficult to take a piece of it. But the other parts, the kind of the carbonate-rich areas and the siliciclastic-rich, the shaly areas, they're much softer. And so if you step back from the outcrops and you look at it from a few hundred meters away, what you see is kind of a cliff where you find the banded iron formation. Then you see a kind of a shallowish slope where actually you've got the kind of more carbonatey-rich part.
Sure.
Then you've got another cliff, maybe for another part of banded iron formation. Then maybe you've got a bigger slope, because maybe you've got a little bit more carbonate in this part, or maybe a little bit of shale or something. Then maybe you've got a really small little part of cliff from the banded iron formation. And so what we actually did is we kind of logged what is the weathering profile. I mean, so when I say like a slopey part, it means that it's kind of weathered there. And whether it's steep cliff, it's kind of what we would call that hard, or indurated is the kind of fancy word for a hard thing that's difficult to erode.
Oh, of course, there's a fancy word for it. Yeah, I didn't. Okay, indurated. So this is the people could imagine, I think visually, the Grand Canyon or something on a small scale, where we've got cliff forming units and then slope forming units, and you've got shales that are the slope forming ones, and you've got either sandstones or limestones typically are the cliff forming ones. But I think anybody who's been in the Western United States, who's been in any of these kind of arid environments with a big canyon in it, can imagine that cliff slope thing. But you're just looking at this on a much smaller scale. Like, what is the height of the cliffs? Are they a couple meters or less than that?
No. Well, the cliffs, maybe the cliffs
like
are
individual ones?
up to maybe 5 meters of cliff. So we were kind of logging over.
That's about 15 feet for the Americans in the audience. Yeah.
Sorry. About maybe 80 meters. Feet, I don't know. So like maybe 100 meters. That's the kind of thickness of the units
total
that we were logging.
Okay. All right. Gotcha.
Yeah. So maybe 300 feet. Something like that.
And so then that cliff slope, the relative height of the cliffs and the slopes are then in your model. These are related to eccentricity, or their orbital dynamics. These are Milankovitch cycles represented in the rock record.
Not yet.
Okay.
Not yet. Not in the model. And all we did. So basically, what we did is we kind of measured the thickness of all of these cliff slopes and cliff slope. And we also we kind of stepped back and we gave the cliffs and the slopes, we kind of compared them to each other. So basically, the steeper the cliff, we would give that a number. If we had a scale of 1 to 10, for example, we would give that a nail. If it's super steep, super sharp, we'd give that a number 1. For example, and the slope, if it's like really shallow, we would maybe give that a number 10. And as the slope, I mean, it's qualitative, right? I mean, we would give them numbers, and we would do it in a little. So it was me and the guy, the other researchers from Utrecht. So there was a little group of us, and we would all do it independently, and we compare our numbers. So we logged it, the actual thickness of all the different units. And then we would kind of qualitatively give numbers to how steep the cliffs were and how shallow or not the kind of slopes were.
Okay,
And so we
gotcha.
actually, I mean, it's super simple. I mean, crazily simple, actually. So we came up with this kind of, essentially, then you can kind of create a kind of wave function with that data. And you can do some kind of statistics on it
So you
to
can basically
see.
say at any point in the column, what is it, a cliff or a slope, and what gradient is it between super vertical sharp cliff and super flat weathered slope. So then you can kind of say there's an oscillation between 0 and 1, and I think that's the wave you're referring to, right? Is it somewhere between 0 and 1 here, or somewhere between -1 and 1? And any point in this period, you can connect the dots there and basically make a curve, a wiggly curve out of this vertical section, right? So then you're doing that, and you're doing that in one place or multiple locations and matching them up.
Well, so what we did is we did it in one place, and we did that in multiple locations over about, for the first study, we did it over about 300 kilometers.
Oh, right.
Turning that into
Okay.
miles, no idea what
Oh,
that is.
yeah, whatever,
I
doesn't matter.
mean, it's
But
probably 200 miles,
so
something like that.
the same units, though, the
So
same rock
the same,
package.
exactly the same cliff is kind of exposed over, I don't know, 200 miles or
Okay,
something like
gotcha.
that in South Africa. And it's relatively well preserved. I mean, it doesn't change too much. And we showed that this kind of cliff slope relationship stays the same. That actually represents all of the exposure. There's not. It's not like we stopped at that because we were tired or something.
Yeah,
It
that's
was
it.
that was it, and because the rest of it is just not exposed. So we did everything, and what we showed is that this pattern is consistent over the whole basin. I mean, once you show that it's consistent over a very large area, it means that there must be some large-scale forcing behind it, essentially.
meaning
So
meaning
we use
some very large scale climate forcing. It must be a very large process. It's not one stream coming in one area dumping a bunch of sediment randomly. That whatever is happening is affecting the entire 300-kilometer basin, which is a large body of water that's doing this, or a large coastline that everything is impacting all at the same time. Okay, so then that allows you to kind of put these lines, which might be orbital or related
Well,
to
yeah,
Milankovitch
all
cycles.
that allowed us to do was to show that there is cyclicity. So we proved that actually there is periodicity. So the cycles repeat, and they repeat on kind of like 5 meters and 20 meters,
Okay,
from my memory,
and there's a
something like that.
big this over a big range, 5 meters, 20 meters,
Over,
over a big range.
yeah,
But
over a massive range, yeah.
this brings up
And so,
time then probably, and if we get this
yeah,
is where
exactly,
this
exactly.
is
So, I mean, at the moment, we've just got depth. We've got meters or feet or
of
whatever.
sediment. Like we're talking about a
Of
package of
sediment.
sediment thing. Okay, all right,
Of
perfect.
sediment. And we show that there is cyclicity. That's the first. I mean, we show that these 5 meters, they actually repeat constantly throughout the sediments and laterally over huge distance of the most distance we can measure in this whole thing. So it's the same. And so we think, okay, there's something big behind that. And yeah, like you say, what we need to do now is convert meters to time. And the only way to do that,
Which is for the listener, this is now depositional rate, because we're dealing with sediments. We have thickness. We need time. And so we're saying, how fast did this thing get laid down? And if my understanding, Josh, correct me where I'm wrong here, but is that the BIF community broadly was of one or two camps. Like people thought that these were deposited either really, really slow or really, really fast, and a huge range in between them. Like we didn't know, or we don't know. We did not know before this work how fast banded iron formations were actually laid down the sediments themselves. Is that accurate?
that's completely accurate. I mean, I think probably one of the most cited studies about the origin of banded iron formation, one of the, maybe not the most cited, but maybe the most known, is one of the earliest studies by a guy called Cloud. He was a prophet at Harvard. And so he said in his original work that banded iron formations are probably related to, the production of oxygen in the oceans by cyanobacteria. These are photosynthesizing cells, essentially. Like they photosynthesize light and they produce oxygen. And so this oxygen then goes into the ocean. The ocean at that time, before there was a lot of this photosynthesizing material, they were anoxic. There was no free oxygen. So if you have anoxic, without free oxygen oceans, those oceans can actually dissolve huge amounts of reduced iron. So iron can be in two different...
Reduced iron, 2 plus iron, not 3 plus
2
iron.
plus iron.
2 plus
not
iron.
3 plus is oxidized iron, 2 plus is reduced. And so 2 plus reduced iron can dissolve at huge amounts in water that does not have free oxygen in it. So the cloud hypothesis was that if you start to produce oxygen by cyanobacteria, this oxygen then can be used up by the iron to change the iron from 2 plus to 3 plus. Okay, because the idea originally was that the cyanobacteria that produces the oxygen, probably the oxygen was toxic to them. So actually, it was quite lucky that there was a whole bunch of iron around to use up that oxygen.
Yeah,
so it was a
okay.
waste product from the cells. It goes straight into iron oxidation. So iron changed from 2 plus to 3 plus. When iron is in the 3 plus state in the ocean, it becomes insoluble.
Okay. And precipitates out
And so
as...
it means it precipitates as like an iron oxide mineral.
Okay, perfect. So in this model, we've got cyanobacteria in the ocean. We've got an anoxic ocean, which is great because cyanobacteria don't want oxygen around, but they produce oxygen, and the ocean is loaded with iron 2 plus, and these cyanobacteria produce oxygen. That oxygen gets used up by oxidizing the iron, going from 2 plus to 3 plus, in which case the iron precipitates out, bonds with the oxygen, and forms some mineral substrate on the seafloor, which ultimately becomes the banded iron, in the banded iron formation in this case.
Yeah, exactly. So that's the original model for the origin of banded iron formations. And so based on that model, I mean, there's a period in Earth's history where we think that the oxygen rose like significantly in Earth's history, like in the atmosphere. There's anoxic atmosphere, and then there was kind of a more oxygenated atmosphere, which kind of suggests that there was a lot of cyanobacteria around producing a lot of oxygen. So they would oxidize the oceans first and then the atmosphere. But if you have a lot of cyanobacteria oxidizing the iron, you essentially should precipitate out, you should crystallize the iron essentially very quickly from the oceans. This is where this idea that basically the banded iron formation should have been formed, you should be able to do like 100 meters per million years.
Oh wow, that quick! 100 meters per million years. That's the model.
I mean, that was the original idea from the original model, and that's been kind of carried through. Even today, people are still suggesting that.
Wow. Okay, so that's extremely fast.
I mean, it's crazy fast.
Fast, right?
Because they think that basically that if you have a lot of cyanobacteria, you just dropping iron out of the ocean like crazy. I mean, that means the ocean must have been really turbid, I imagine, just like full of iron oxide, just falling out of it.
I mean, that's insane. I'm having trouble calibrating here because aren't normal like background sediments on the order of a few meters per million years, like your average shale or sandstone or something? I don't actually know. Deep ocean.
Speak about ocean sediments, we can even meter per million years is a reasonable kind of
okay for deep ocean stuff, which is what this is what we're talking about here. Is
this kind is probably shelf. I mean, maybe not super deep, but a shelf. I mean, but still that kind of rate would not be crazy. I mean, 10 meters per million years is also not crazy, but they were suggesting 100, which is, I mean, at least an order to 2 orders of magnitude more.
Extremely fast. Yeah. Okay. All right.
Which
perfect.
is like really fast.
Okay. And
this is, this is the whole ocean. It's not, we're not speaking about a lake.
Okay.
We're speaking about the whole Earth, essentially.
It's just just the scale of these processes is just unbelievable to think about. So, all right, so you've got this banded iron formation sequence that you've mapped. You've looked at the thicknesses, the cliffs, and the shelves, and you've qualitatively estimated those. You've got now a pattern, a sort of a wave function through the log of this thing that says, okay, is it a cliff on one side? Is it a shelf on the other side? And it's somewhere in between there. Then how do you get these numbers? How do you get rates?
Rate? Yeah. I mean, we were really lucky. I mean, there is actually basically small, tough horizons. I mean, which is like a volcanic ash layers inside these banded iron formations. They're kind of hidden inside shales, or I mean, because these rocks, they're deposited in the ocean, and it's all kind of weird rock types that you don't have nowadays. And so there's shales deposited inside the banded iron formations, and some of these shales, they contain zircons.
Okay, right. And this is really fortuitous. And actually, correct me, Josh, but I think isn't this fairly common that there are? I mean, we have these in central Pennsylvania. We have the intro level class that I used to teach takes a field trip, and we look at bentonite layers, which are bentonites are just volcanic ash that's been weathered, and they're maybe millimeters to centimeters thick in a package of well, they're in carbonates and shales, but they're layered in there, and you can kind of see these things. And they're bentonites. They're a volcanic ash layer, and the ash will have zircons in it, and the zircons date the timing of the eruption. Is that the same thing you're finding here in this weird disaggregated shale, or is it different than that?
Well, essentially, it's the same in that, apart from the fact that the bentonite, I mean, in Pennsylvania, or I mean, a lot of younger rocks.
Yeah,
I mean,
you have the same bentonites up in Quebec
layer.
too.
Yeah, we do. But you can kind of see a layer that's kind of clay, maybe, or maybe it's got a weird color or something like that. In the banded iron formations, it's kind of like a black shale. So it doesn't look like a normal bentonite at all. Not at all.
So how do you identify it in the field? Or how did you get zircons
identify it in the field? Well, what we did, we were lucky, is that the Dutch people, they got enough money with their funding. I mean, the Dutch Science Foundation funded a drill core.
Oh, okay.
So we actually drilled our own drill core through the banded iron formation.
Wow.
We did about, I think it was about 200 meters.
Wow. Okay.
Of
amazing.
Drill core through the BIF. And so with that, what we did is we found the shale units. So we tried to do it in the field, but the shales are recessive, essentially. They're in these kind of shallow sections, and they've been mostly weathered away. And they're covered in grass. It's very difficult to get at it.
Actually, sample
you can't really
it.
see it. You can't sample it, and you can't like target it. And so, without the drill core, we'd have been lost. Really, really, completely lost. We were really lucky that the Dutch group they got a drill core funded, and so we drilled through this banded iron formation, and we like chose the location. We spoke to the farmer, so we were drilling on somebody's land, obviously.
Yeah.
We got some really crazy stories about this. I mean, the guy
I'm sure.
Yeah, I mean, we were in South Africa. The farmer who had the land that we used for the drilling, I mean, he had a game reserve. So we were actually driving through, I mean, a game park, essentially, to go to the drill site. I mean, seeing all these different antelopes and, I mean, deer and zebra and stuff. Really cool. I mean, really, really cool. And so from the drill core, we were able to do things like XRF measure. We were able to kind of measure different elements in the different units, and we can kind of show that there's a higher amount of zirconium in this particular horizon, and we could sample it, then we could try and separate zircons. And so that's what we did. We separated zircons from quite a few different layers inside the banded iron formation, and then like visually, we could separate visually looking at the zircons. They looked really pristine. Like, you know, when you look at zircon from ashes, volcanic ash, they're really well formed, essentially. They look really, really nice. Zircon that's in a sedimentary rock, they're often rounded or eroded because I mean they've gone through
weathered,
some sediment
tumbled down a stream bed basically and had all the edges knocked
they kind
off.
of look rounded.
Okay,
Whereas
gotcha.
these ones looked kind of with sharp points.
Gotcha.
And that's
Okay.
always a good sign
Yeah,
to
yeah,
show
yeah.
that maybe you've got more ash type zircon. And so then we basically dissolved those, did high precision dating on them. It's much more annoying, much more annoying than it sounds.
Yeah.
I probably dated
Yeah.
about, I don't know how many, about 160. It probably took me 2 years.
Yeah.
But in the end,
Just a monumental amount of work.
a huge amount of work. But in the end, we got some really good results. And so we could really be confident that we had reasonable ages for all of the different ashes that we tried to date. And with these ashes, we could kind of calculate a deposition rate
Okay. So in
for
the
the Bantaline Formation.
the visual here, I think for people is that you've got 200 meters, let's say, drill core, where you've mapped all these sort of cycles throughout that sequence. And you have what, 5 data points, 8 data points? How many do you have? 4 data points of
I think probably 4.
4? Okay.
4 data points.
So 4 data points that have ages. And is this the one that's like 2.5 billion year old BIF? Or is this the one that's...
Yeah, well, it's 2 point, if we have to get back to our precision.
God, okay, let's be precise, Josh. Yeah, what is it exactly?
2.48, I guess, is
okay.
the
Yes,
earliest part, down
excuse
to
me.
around about 2.46.
Okay.
So,
Okay,
that's
good. So,
that kind of time.
so you have a 20 million year range, but you have basically tie points, and those tie points have uncertainty on them. So you can say, oh, the top point is 2.46 plus or minus something, and the bottom is 2.48 plus or minus something, and the middle is 2.473 plus or minus something, and you can kind of fit an age model through there with uncertainty. It's kind of the key point, right? Like you can get a depositional rate plus uncertainty at any point in that history, in that full 200 meters with 4 tie points between it. So you're kind of interpolating between data points, and there's this cool Bayesian statistical model that people use for these types of things now. But what's the depositional rate? You were talking about the original model, the cloud model, the famous Preston cloud model that's sort of 100 meters per million years.
Per million years.
Very fast.
So we got 10.
10. Okay.
Basically.
Okay.
10 meters per million years. And so, ours is based on data, real data, where the 100 meters per million years is a model, not actually based on any data, to be honest. Other papers have tried to speak about that, but they've kind of discussed it and then made kind of little cartoon sketches, and then
Yeah. But this is real
included the
geochronology.
100
This is real zircon, uranium, lead. So the real stuff. This is, all
this is the serious
facetiousness aside, this is the gold standard of geochronology. We cannot do better as a field than zircon, uranium, lead geochronology like this. And so you're getting 10 meters per million years through this package rock. So much slower. Then bring us full circle to the cycles now. What is that? These 5-meter cycles or whatever, 20-meter cycles, whatever they were, what does it mean for Earth-Moon distance, and what does it mean for precession?
So the 5 meters is that it's not exactly 5. It's a little bit less than 5 meter cyclicity. That actually converts with our depositional rate to about 400,000 years. And the longer cycle, that converts to about 1.6 million years.
1.6 million.
And
okay.
so actually 400,000 years is exactly the time period you would expect for eccentricity. So on the modern Earth, the eccentricity, which is the orbit, whether it's more elliptical or more circular, those have principal periodicities of 400,000 and 100,000 actually. So we found the 400,000 one, and the 1.6 is actually another longer period eccentricity signal. It's not unusual to find that in a long scale record. So the scale that we were logging at is at the kind of maybe 20 centimeter resolution. We were not doing because we were looking at the slope or how steep the cliffs were. We were not able to identify cyclicity at higher frequencies.
Higher frequency, sure, gotcha. Okay.
Which is what you need for looking at precession. Modern precession is 24,000 years.
Sure. Okay.
So our logging was not 400,000 years, which is an eccentricity timescale. that's kind of the limit of the time period we can see
Okay,
with
gotcha.
that kind of logging.
Yeah. Okay,
So we
gotcha.
actually found it, but I mean, we were really impressed because it's crucial. I mean, people think that the eccentricity, which is 100,000, 400,000, and then there's a few longer time periods, that's kind of considered the Earth's metronome. That's what it's kind of called. People think that the eccentricity signal, this 100,000, 400,000, that's kind of consistent over all of Earth's history. And so that's actually what we needed to find that. So if you find that, people can be more convinced that you've really got Milankovitch cycles.
Yeah. I see. Okay, yeah, because those should be back on.
Because
Those should be there.
those should be there.
Okay,
And so
gotcha.
we found it.
Yeah.
So
Interesting.
we were really happy. I mean, we're super happy with that. But I mean, that was the first study we did, was just proving that there is Milankovitch cycles there. And after that, we kind of wanted to go a little bit deeper. We wanted to try and find this precession thing, because that was the real
Which is the now
goal.
we have to map at the sort of centimeter scale and look at
Yeah,
these
well, now we need
cycles
to really
much
go
more.
more precise.
Okay, gotcha.
We need to look at things that are cyclicity on a more centimeter scale.
Okay,
Exactly.
gotcha.
And we could not do that in South Africa
Okay.
because the rocks don't allow us to.
Yeah, I see what you're saying. Okay. So the first thing in South Africa is I hadn't really appreciated this is kind of confirming Milankovitch cycles, because you needed to see this 460,000 year cycle, and you saw it with the mapping that you did, and the sort of, as you described, the relatively simple mapping and the geochronology, the 2 years of work geochronology. So then you decided to go to, is this where we go to Australia? Is this where we go to Hammersley?
Yeah, exactly.
Okay.
It's when we go to Hammersley Basin in Australia.
Okay, which is a huge iron mining district. I mean, these is an astronomically big, no pun intended, iron deposit there in the Banded Iron Formation. A very, very famous location. And here you have really big cliffs of Banded Iron Formation exposed,
what
right?
you have there, which is really important for us, I mean, is these gorges. I mean, it's a bit like the Grand Canyon. Well, it's not quite as impressive as the Grand Canyon, but it's that kind of style. There's these rivers flowing through, I mean, arid desert in northern Western Australia, right on the edge of the Pilbara Craton. So, I mean, these are old rocks. There's sediment sitting on the side of these very, very old rocks. And there's rivers going through that, cutting really beautiful cliffs through.
Spectacular. Oh.
I mean, that is really, really spectacular. Cliffs through these rocks. And so there's actually, like the Grand Canyon, there's kind of paths down the cliffs.
Okay, yeah.
So you can kind of walk next to the rocks. And they've just been polished by the water. And really, really cool, really beautiful. It's a national park. It's so nice there. And we were so lucky to just we were doing field work there, camping in a national park, being paid to just go and hang out on these cliffs.
These beautiful rocks. I mean, that's spectacular. So,
I mean, really, really nice.
So in this place, you did
we found,
the more precise logging, I'm guessing here, to kind of get, more precise logging, and then the same kind of geochemical sampling, or geochronological sampling, targeting zircon-bearing beds, basically, or?
Yeah, we did the same. We did more hyper-resolution logging. I mean, really centimeter scale. We tried to measure the concentration of different elements using a XRF, like a little, like a machine we took into the field, and it kind of gives you the chemical composition of the rocks. It's not super precise, but we did that to try and get a kind of a record through the rocks. We did logging, and for the geochronology sampling, we were also, again, really lucky. The Geological Survey of Western Australia, they have drilled drill core. Oh, I don't know if even they've done it, but they've got a drill core in the Geological Survey that goes through all of these units.
Oh, right. Okay.
So we didn't have to do it ourselves.
Gotcha.
It's also in a national park, and
they
were really against us sampling, and they didn't really want us to definitely not bring drill rigs and do stuff like
makes
that.
sense.
But there was already drill core available, and so with collaborators in the Geological Survey, they allowed us to sample the drill cores, and so we had exactly the same stuff. We found the same kind of layers as we did in South Africa, with the zircon-bearing things, and we also dated them in the same way, and we found exactly the same depositional rate, exactly the same. I mean, the rocks are deposited at essentially the same time periods. I mean, precisely at the kind of million year level, back at 2.4 billion years. I mean, which is quite crazy. So the depositional rate is exactly the same. There's also small inflections in the depositional rate that happen at exactly the same time in the two areas, Australia and South Africa. So we were super happy, really impressed by the rocks, by the results. And so this 10 meters per million years is consistent.
Matches
And so
across these two packages of rocks. Okay.
Matches
good.
across the two continents, essentially. So it gives you extra confidence that it's kind of correct. The cyclicity, we found again the 400,000 years. But now, with this cliff section, we could find the 100,000 years, which is the next time period, the next periodicity of eccentricity. And then we could also find another signature, another cyclicity that was being modulated by eccentricity. And so modulation, that's when that's this interference pattern.
Okay. Yeah.
So
Where it's either making it go bigger, it's sort of, if you have it's something that's oscillating up and down, up and down, up and down, every once in a while go too far up, or once in a while it won't make it all the way up because it's either being interfering positively or negatively with something else, right? So that's the modulating effect. It's sort of suppressing it.
The modulating effect, yeah.
Yeah.
Exactly. So when you see the 400 or the 100,000 year signature really well expressed, this other signature is also super well expressed at that same time.
Gotcha. Okay.
When the 100, so what I mean by that is kind of when it's well expressed, it means that in the cliff we're looking at, the shaly units are really obvious.
Okay. I see what you're saying.
Actually.
Yeah.
And so that means that this 100,000 year cycle is really well expressed.
Yeah,
and so
okay.
Then there's really obvious other layering at a higher frequency inside that area. When the 100,000 year cycle is less well expressed, it means that kind of the difference between the steep cliffs of the BIF and the kind of more shallower slopes of the shaly stuff, it's less distinct. And at the same time, the small layering is also a little bit less distinct.
Okay.
so
These subtle differences matter a lot for these things. Yeah.
But this combination of both of those two things was super important, really, really important, because it shows that there's this link between the higher frequency cyclicity and the lower frequency, the 100,000 year. And so we could use that as evidence that we have precession, because we know that eccentricity and precession are linked in that way.
And have this exact, and on the modern Earth,
because
eccentricity
and on the modern Earth,
have that
we
same
know
sort
that
of
they're linked, and
interference.
yeah, exactly.
Okay, interesting.
So that allowed us to be confident, because I mean we don't know the periodicity of precession, because we don't know the Earth-Moon distance.
Right. So yes, you're trying to, again, to go back, you're trying to calculate. We know that the Earth-Moon distance, we're going 2.46 billion years ago. This is a period where I think continents are stabilizing for the first time, or just 100 million years before that. They stabilized actually for really the first major time. And you're going back there, we don't know the Earth-Moon distance. We know it cannot have been moving away from Earth at 3 centimeters per year as it is today, but we don't really know where it was. So you use this precession. You don't know the cyclicity of precession. You don't know whether on the modern Earth it's 26,000 years, something like that. You don't know what it is back in time. It's a free parameter, but you are calculating it now. You're showing it in relation to a 100,000 year cycle. And what is it? What is the precession that you measured, and what is then the Earth-Moon distance that you calculate from that?
So I mean, it's a little anticlimactic, I guess. I mean, we're speaking about these fancy we're speaking about solar system processes, and now I'm going to say, precession was 11,000 years.
Well, that's different.
Okay, great.
That's half.
That's exciting.
It's half.
It's half.
It is.
Yeah, we calculate it to be about 11 to 12,000 years, something in that kind of range. Which is completely different to the modern. Yeah, it's basically half. And so if you put that into the calculation for how you can work out Earth-Moon distance, that suggests that the moon was about 60,000 kilometers closer to the Earth than it is now.
Okay. And the Earth-Moon distance right now is 380,000 kilometers. And so you're saying it's 320,000 kilometers roughly,
It was about 320,000 kilometers
plus or
at
minus
2
several
point.
thousand kilometers, probably somewhere in there.
Yeah.
But you're saying, okay, it's significantly closer, 60,000 kilometers closer. So Earth was a lot closer, it'd be a lot bigger in the sky. And also let's come full circle here as we kind of wrap this story up, because I mean it's just amazing to me that you can do this with geochronology. This is the cutting edge geochronology that if we did not have the tools and instruments and the techniques that you and your colleagues in your field have developed over the years, we could not do this work. We have to have ultra precise geochronology in order to do this type of work that you're doing. But 2.5 billion years ago, Josh, how long was a day?
Well, we calculated it and it was about 17 hours.
17
17
hours.
hours. So that means the Earth was spinning much, much faster
Much faster.
than it does now. Yeah. I mean, crazy. I mean, you know what? I'm just completely, because for me, I'm a geochronologist, right? So I've lost a little bit of that awe from dating things because it's my job.
Yeah.
I mean, it's what I do.
Yeah.
That's what I do every day. So I mean, I find it cool, but I was so amazed that we could speak about solar system processes from just making very simple measurements in the field. We measured the thickness and how steep these cliffs were.
Yeah.
I mean,
How steep
of
is it?
some
1 to
rocks
10, Josh? You
yeah.
do it, and then I do
I
it,
mean,
and then we
that's
compare
it.
notes. Yeah. It's true. It's basic. It's basic. I mean, it is really. You're
I mean,
right.
it's
It's an amazing
observations.
story.
It's making geological
It's
observations.
basic,
And really,
fundamental geological field observations with a very high-end geochronology technique that's been developed over decades and generations to get to a precision level that allows us to do this. So the fanciness of your geochronology, high precision geochronology world is not lost on me yet. And so just being able to do this geochronology, I mean, you're getting data points that are spectacularly precise. You're getting ages that are 2.4 billion years ago, and it's plus or minus 600,000 years. And that's like not the best data point you have. That's moderately good. That's a spectacular precision on these ages. So it's not lost on me, although it is simple. The power of that geological intuition, simple observations, and then some pretty advanced physics to calculate these things, I'd imagine. But it's such a cool story. Man, it's a cool story.
but for me, that's the kind of, that's what gets me excited about geology, is the fact that you can speak about these like global or maybe even solar system scale things by having an interesting thought experiment.
Yeah, that's right. That's
actually,
right.
you can just test models about global processes. I mean, with fancy tools for sure, but what you need is to have a like an innovative idea. That's basically it. That's it.
And there's the
And
good
you
news
can
about
go
our
and test
field
it.
is it's a pretty young field comparatively to other fields of science, and there's still a lot to be explored. And we have a huge amount of time. We have a lot of Earth processes we do not understand. I mean, I've talked about this before. I'm super excited to be a geologist and geology professor at this point in time. There's just so many problems to solve that are so interesting. So I think this is a great example of some of the really cool science that can get done. So real quick, what's the reception been on this work? I mean, I know from talking to you offline that it's some of it's been very positive, and some maybe ho hum. But what's in aggregate? What are you
Actually,
feeling?
so I would say the main positive thing that's come out. Well, I mean, this work is getting quite well cited. So I mean, it means that people are at least reading it.
Yeah,
which is good.
that's great.
What I'm most impressed by is that there's been follow-up studies by astrophysicists or like people studying like the evolution of the Earth, doing models and trying to calculate how the Earth-Moon system has evolved over time based on modeling. This is really, really complicated because the Earth-Moon system, I mean, as we know, that the Moon and the Earth are related in the tides a little bit. And so there's a link between the tidal system on the Earth and the Moon. That's actually what's controlling the Earth Moon distance, and that's kind of making the moon move further away over time. But to model that back in time, to look at how this tidal influence has affected the Earth Moon distance, you actually need to know the structure of the continents, because you need to know the ocean basins. You need to know the structure of the ocean basin. We really have no idea. Like when you go back into the Cambrian, which is 500 million years ago, we don't fully know exactly what the ocean basins were like. And then when you go back into the Precambrian, like 2 billion years ago, we don't really have any idea. It's really, I mean, we don't know how many continents there were,
Right, or what volume were there, or where they were. Yeah,
where
for sure.
where they were. We don't know. And so that actually plays a huge role in what the ocean is doing, right? I
Right,
mean,
right,
because
right.
ocean currents are really related to where the continents are on the Earth. I mean, if you have a big, like if you have all of the continents kind of stretching like in a thin line from the North Pole to the South Pole, that's a massive effect on ocean
Right,
currents.
right, right.
Whereas
Yeah,
if you
which
have them
then,
kind of
okay,
all
so I
around
see
the
where you're going.
equator,
The oceans have a big influence on the moon, and so therefore are people reverting your model or taking your data point as a calibration point for their models of
well,
these
actually,
cycles back in time?
they're plotting our data on their models. They're not. I mean, the astrophysicists wouldn't use our data as a calibration point. No, no,
No.
no. But actually, but our data is in like perfect agreement with the most advanced models. It's not that they are perfect in any stretch of the imagination, because we just don't know,
No, no,
right? We
no,
just
no.
don't know exactly what the continents are
Yeah,
like.
that's right. All models are
But
wrong.
the
Just how
best,
wrong are they is
yeah.
the question, right?
So maybe we're also wrong, but we are matching exactly with what the best estimates are at the moment. And so, I mean, for me, that's the kind of the coolest thing. I mean, it's kind of all aligning, I guess.
That's great
Yeah.
to hear. Yeah. Well, Josh, I mean, okay, we've talked for many hours about science, and we've talked for a long time already on this. But I think we're going to keep talking about geochronology and go into the weeds, certainly deep, deep, deep into the weeds in geochronology. But I don't know the answer to this question either, which is our traditional closing question, which is, what has been your best day as a geoscientist?
It's a difficult one. I mean, it's difficult. It's a difficult one because I mean, I've worked on loads of cool projects
You've
and
been
had
all over the
loads of
place,
cool results.
including with me up to Acosta. You were,
Yeah,
yeah.
I mean, you with you and your dad.
Yeah, yeah,
I
that's
mean,
right. That was
we
fun.
can't forget Ron.
That was
We
pretty
can't
good. That
forget
was
Ron.
pretty good.
And I mean, catching massive pike in a caster. I mean, that's a pretty special moment, I have to say. On a fly rod. I mean, with a can,
So yeah, the beer can lure. Yeah, yes,
with a beer
that's right.
can.
Anyway,
For me, it's got to be these like these views, these kind of like I've had a few times when I've been in the field. I mean, I've been recently in Namibia. When you're just you kind of hiked to the top of a kind of a lookout or a mountain, and you're sitting on these really cool rocks. I mean, that are telling you about the kind of the development of complex life. And then you're looking out over the desert in Namibia, and there's kind of ostriches just running across the desert, and you're just thinking, how am I paid
yeah,
to do
yeah,
this?
yeah, yeah.
You know, you're
How lucky
thinking,
am I? Yeah.
like, how amazing is just the Earth, and being able to kind of study the Earth and go to these really cool places. I've had this quite a few times. I mean, in Acasta, it's just spectacular, and just sitting there and looking out over the landscape, or just chatting in the evening to you and your dad. I really loved it. And I mean, in Namibia, South Africa. I mean,
Yeah, you've been
for me,
all
it's just
sort. You
been a
you have
few
you
days.
have been
Just
to some of the most classic geological locations in the world to do
yeah, I
geology, not
mean,
just for fun, but to do the actual work. Which I think I agree. It adds another layer when you're there working, quote unquote working, and it doesn't feel like work. It's spectacular. You know, you're standing there. You're like, I know about this area. It's not just you're not just rocking up to some national park that you don't know much about and just looking at the landscape and saying, oh, it's a pretty view. You actually have done you've done the reading about the place. You understand the rocks. You know the questions. You know what you're there for and what you're there after. And you're after something you're passionate and interested about. It adds like another bunch of lenses to the view of the landscape, and it just makes the landscape kind of pop in your mind a little bit of the importance of it and the history of it. So, I mean, it's why geologists tend to look up and spend time reading about the places they're going to go and the rocks they're going to see before they go places, because it adds that layer of appreciation to it. Except it's this on a monumental scale. So, well, we
spend way too much time on Google Earth.
Yeah,
like
that's
looking
true.
At the satellite views of
true.
The beautiful locations we're going to go and see.
Absolutely. Well, it's a bit of a cop-out, Josh. You didn't really actually give the answer a single day, but we'll take it because it's a pretty good one. I mean, it's a pretty good theme. So maybe next time you can think about it a little bit more and have a day that
get me down to a particular day.
But there must be a day in the lab, right? When you get a data point and you're like, ooh, that's exciting. That's an exciting data point as well when things are working.
I would say more when I came to Geneva, when I came to Montreal. I mean, it's more like I had to do it all on my own. You know, I had to set up a lab, and when I started measuring, I mean, it's not very exciting when I start to measure standards, and I got the right age.
Yeah. You're like,
I mean, I was just so happy, you know.
Yeah.
And I measured blanks.
Yeah.
And they were really good.
Yeah. That's
and
right.
Or even just the first time I got a beam on the mass spec.
On the mass spectrometer, you're like, oh, look at this. This is great.
It just feels so good, actually.
Things are working.
I mean, it's not necessarily just I measured this great point, just the fact that I got it to work. You know, and things are working as I hoped, and I mean, all of the previous work has actually, you know, come to fruition a little bit with some really cool stuff we've done, but just making it work, I was really impressed.
Yeah.
by, you know.
When things work, it's amazing. Oh, I feel you on that one. That's a good one too. All right. Well, Dr. Josh Davies, Professor Josh Davies, Joshua HFL Davies, if you're looking him up on Google
HFL,
Scholar.
that's it, exactly.
My good friend, Josh Davies, and colleague and co-author. We will have many more discussions like this in the coming years here, focused on geochronology and all things deep topics and deep time. But the Earth 2.4 billion years ago, the day was 17 hours long. So that's a pretty cool visual. That's a pretty cool visual based on the work you've done there. So awesome. Hey, man, thanks for the story. Look forward to talking next time.
Yeah, I'm excited.
All right,
Talk to you later, man.
See ya.